Alright, so in this video I'm going to be explaining this important paper with the title CoCo, a coupled contrastive framework for unsupervised domain adaptation graph classification. This ICML paper in 2023. Although graph neural networks have achieved impressive achievements in graph classification, they often need abundant task-specific labels, which could be extensively costly to acquire. A credible solution is to explore additional labeled graphs to enhance unsupervised learning on a target domain. However, how to apply GNNs to domain adaptation remains unsolved owing to the insufficient exploration of graph topology and the significant domain discrepancy. In this paper, we propose coupled contrastive graph learning, which extracts the topological information from coupled learning branches and reduces the domain discrepancy with coupled contrastive learning. CoCo contains a graph convolutional network branch and a hierarchical graph kernel network branch, which explore graph topology in implicit and explicit manners. Besides, we incorporate coupled branches into a holistic multi-view contrastive learning framework, which not only incorporates graph representations learned from complementary views for enhanced understanding, but also encourages the similarity between cross-domain example pairs with the same semantics for domain alignment. So the challenge is how to sufficiently extract topological information under the scarcity of the labeled data. The other challenge, how to effectively reduce the domain discrepancy in the graph space. You see the overview of their framework. We have source graphs. Here we have source graph. Here we have target graphs. Now here is a cross-branch contrastive learning. So we have, it could be, the two branch could be GCN branch and HGKN branch. You could either use graph convolutional or these graph kernel networks. From both of them, you find the pseudo-label assignment. And also you can have a GNN classifier. So we utilize a graph convolutional network to implicitly extract topological information. The node representation is updated like this, and here we have this readout. The graph kernel network branch, because GCNs are insufficient in collecting sophisticated high-order structural information such as rings. It is anticipated to explore graph topology in an explicit manner as a complement. So we introduce a hierarchical graph kernel based on graph kernel. At each hierarchical layer, it compares each R-hop subgraph with a learnable filter graphs via the graph kernel. This is similar to the work of Professor Bronstein in Oxford University. He published in IEEE 2025. It's very similar because here, for example, here we compare the discrete input graph and the filter graph. Of course, they had Professor Bronstein had much better formulation. He had expectation over those kernels, and so this is the same paradigm. But now here we have R-hop subgraphs. R-hop is same as Professor Bronstein, and filter graphs. But for Professor Bronstein's approach, we learn the filter graphs. And we find graph kernel, then finally attention pooling and this, because we want to coarsen the graph. We update the node representation by concatenating all output of filters. to fully exploit graph topology information derived from two branches, we formalize the multi-view contrastive framework, which contains both cross-branch and cross-domain contrastive learning. But what is cross-branch contrastive learning? Considering that the model learns graph semantics from complementary views, we contrast the graph representation from two branches to exchange their knowledge mutually, which enhances discrimination learning on target data under labeled scarcity. So for each graph in a source batch and a target batch, we produce the embedding from coupled branches. And they induce this info NCE loss to enhance the consistency cross-coupled branches. To produce label distribution of test data, we utilize enhanced graph representation from first branch to predict the label via a fully connected layer. So we have this overall loss objective. So the output is the GCN parameters, graph kernel parameters, the two network that I said, theta and phi, the two network parameters, and the classifier parameters are the outputs. So these are the outputs that we are learning using CoCo. So you see, when you go from one source to another target, for example, if you go from source M3 to the target M1, you will have, if you compare graph convolution with CoCo, you see CoCo has improvement. So they did it on mutagen dataset, on Tox21 dataset. They did classification on protein, COX2, and BZR when you go from one source to target, from source domain to target domain. And there is also ablation studies on mutagenicity. And this is their appendix that they show expectation maximization perspective.